So since there's two of us, I'm going to do a quick re-intro. I'm Bryton. I work on the network edge and backbone team at Cloudflare. I'm going to start things off, and then I got Mingwei. Mingwei works on Cloudflare Radar, a lot of routing visibility and BGP stuff. If you go to radar.cloudflare.com, you'll see a lot of Mingwei stuff if you search your ASN or look at routing tab or anything like that. So today we're going to talk about route leaks. But specifically, we're going to talk about how we detect route leaks that impact our BGP prefixes. So just a quick overview of what we're going to be covering. We're going to talk about the baseline of what a route leak is and why do we care when they happen. What's the big deal? Then we're going to get a little bit into the Cloudflare network because there's some things we need to understand about simple versus complex peering relationships that Cloudflare has, as well as a couple different types of prefixes that we need to account for. So then we're going to have Mingwei cover the leak detection pipeline itself, and then we're going to kind of touch on some things that we're looking forward to in regard to having less impact from leaks automatically in the future. So kicking it off, what is a route leak? So as defined in RFC7908, a route leak is the propagation of a routing announcement outside of its or beyond its intended scope. And if there was like one phrase or a couple set of words that I would like write up here in like red marker or permanent marker or something, it would be intended scope for the rest of this presentation to kind of think about. And that's because intended scope isn't always necessarily that straightforward. It can change, different types of prefixes and this kind of stuff that we're going to be covering. But a simplified version of what a route leak is, like I hear a definition that I really like a lot, is if you're a network and you take a BGP announcement from one neighbor and you take it and then you send it to another, so two networks on each side, and neither of those two sides are paying you, then you're leaking a route. AKA, if you're taking the announcements and sending them and hairpinning them around, one of those two sides should be your customer. And that's true. Like that's a good simple definition of what a route leak is. But also we're going to go over some leak examples that don't fall directly into that simplification. So why do we care about when route leaks happen? What's the big deal? So if we take like the most typical or basic example of a route leak, where in this case, provider 2 sent routes down to their customer as they should, let's say it's a full table, and the customer takes the routes and they send those routes back up to their provider 1. We know that the opposite of the BGP update path is going to be the traffic forwarding path, right? So the customer is about to get a lot more traffic than they probably bargained for. They probably haven't provisioned the network to handle the entirety of the internet, a full table worth of routing. They probably didn't even configure ACLs to accept the entirety of the internet in their, say, a small ISP network. So there's going to be a lot of elevated latency, maybe just black holing in general bad time for the traffic that's going through this customer hairpin of a leaked route. And then we have incidents. We have to write incident reports. Operators, we have to wake up at like 2 a.m., get paged, and then we investigate. We run a trace route, MTR, and we find that, our traffic that's supposed to be going directly from nearby data centers, let's say Frankfurt and London in Europe, but they're stopping at some ISP in Chicago for a slice of deep dish pizza. So going to be a lot of latency there. It's not going to be a good time. Our customers are upset with us, and then we end up writing a blog about it. So it's not a good time. All right, so let's talk a little bit about the network that we're designing leak detection for, which in our case is the Cloudflare network. Touch on some of the peering relationships and the prefixes that we need to account for when we're looking at route leaks. I promise this is the only marketing slide that you're going to see. I apologize for it. Kind of a copy paste here, but the general idea is we have a lot of data centers spread out throughout the globe. But more importantly is the over 13,000 networks that we directly connect with. When you connect with that many networks at a global scale, there's kind of like pros and cons from a route propagation and leak perspective. So the pro is we send our routes to a lot of different networks. So if there's a route leak, hopefully they're still using our routes. Hopefully that's still the shortest path. Hopefully they're still using them and there's not much impact. But the con is, I mean, we're sending routes to route servers, to IX peers, we're open peering relationships. There's a lot of peers that could leak our routes themselves, right? So we need to be able to see that, recognize it, alert on it, respond. So let's talk about the two types of prefixes that we need to be able to detect leaks for. It's hard to talk about Cloudflare without talking about BGP and Anycast. So Anycast, as probably most folks know in here, it's when you advertise your IP prefixes everywhere or in a lot of places in many data centers. In our case, globally advertise the same set of IP prefixes everywhere. And the goal is take in traffic to the nearest data center to the user. When I wanted to find a visual for Anycast, I wanted something not the typical like multiple arrows to a server. I wanted something with BGP. And I tried to put all 13,000 networks up there, I promise, but I blew up my browser. So here we are with just the tier 1 propagation of an Anycast prefix. So you can see everybody, except for one, tier 1, is getting our Anycast routes directly. Compare that to an example unicast prefix. So unicast is a lot different for us because it'll depend on the data center which tier 1s, which transits, which peers that we have. So they won't have all of our unicast routes everywhere. That's not how we operate. Even though we have a global backbone, that's still the case. So in this case, the unicast prefix, we're sending it to, it looks like 3 or 4 tier 1s, and they're doing the heavy lifting of connecting us to the rest of the internet. So let's talk about how those prefixes map to peering relationships, which is really the important part for evaluating routes and propagation and leaks. So this is a peering relationship that everybody should be really familiar with, and that's just like what I would call true transit or full transit for us. And that's when we send either our Anycast or our unicast routes to the transit, and we say, you can send these everywhere. Give us internet connectivity for all of these prefixes. Send them wherever you please. But I say everywhere with an asterisk, kind of send them everywhere, because in reality, we might be doing some BGP community-based steering, as in, hey, Mr. Tier 1, please keep the Anycast route in this region. That would be great, that kind of thing. But from a BGP relationship standpoint, it's a real transit relationship, even for us. So another one that's really straightforward is just peering. It's the peering that we're all used to. We send our Anycast or our unicast routes to a peer with the intended scope being, hey peer, please send these routes just to your customer cone. If you send those routes upstream to your peers, that's going to be a route leak. So again, those two extremely straightforward. We're all familiar with this. So where it gets a little hairy is what I would call mixed transit and peering for us, otherwise known as a complex peering relationship, where we tell AS65001, please take my unicast prefixes and I want you to be a transit for those. I want you to take my unicast prefixes and send those everywhere. Give me global connectivity for unicast from this data center. But for Anycast, I want you to be a peer. Please take my routes over peering if they're Anycast and only share them with your customer cone. So intended scope of Anycast is only your customers, just be a peer. But intended scope of unicast is global connectivity. This is really common for like a Cloudflare embedded cache deployment, so like a remote data center with one partner network. Obviously, we need global connectivity with unicast, but we just want to serve their customers with Anycast. So from this, we know the variables that we need to account for leak detection. We know that at the end of the day, leak detection relies on having accurate and precise AS level relationship inferences. But we also know that those inferences or those AS relationships need to account for variation per prefix. So we use the Anycast versus unicast example. The intended scope is different for those two prefixes, so that needs to be reflected in the network to network relationships. And another one is per location. We could have a transit session with AS65001 in some remote data center, but we also might peer with them along our backbone. and that's in a peering session. So we need to account for location as well. So to talk about how we actually implement route leak detection with the rules that I've went over, I'm going to pass it over to Mingwei.
So hopefully you get a relatively good idea of how Cloudflare's complex relationship with other networks are in this case, because and we're going to introduce you the ideas, or kind of summarize the ideas of how we build our detection pipelines, and trying to catch the BGP announcements that are not fit into a or expected or intention scope. Some of the overview. So I'm trying to go as high level as possible so that we can give you like a good understanding of everything that's involved in the whole pipeline. So from the left to right, so we're basically going from the source of the BGP messages into alerts. At the leftmost, we're taking BGP data sources. I'll tell you in the next slide. We'll talk about those data sources. But for now, we're taking the best available public data sources and as our kind of a leak detection. And one of the reasons that we're choosing public data sources, not just because they are available, but also because they are representing the views from like outside Cloudflare. So we want to take the potential customers, the potential impacted areas view, so that we know from those vantage points what are the routes looks like, and then the public data sources will be good fit. And then we're turning that into a stream of messages and containing like AS paths and then those community values, and then kind of ship it into the detection pipeline in the center, where we're combining our inferred AS relationships. And then the asterisk, or the emphasis is on inferred. I'll talk about why inference is the keyword here. We're combining inferred AS relationship and the ground truth into this pipeline so that we can make a somewhat informed decision on what's a leak and what is not a leak, and we can give a relative a confidence score on what's the alerts that we need to act on right away. So this is on the very leftmost side, where we're kind of turning BGP data into a actionable like the data streams. So we're taking both route views and REPRIS BGP archive data. And if you don't know about them, route views and REPRIS are the two, I think, the best well-known BGP archive data. They've been operating for over 20 years. And they're basically collecting two types of data. One is the periodical rip downs. For route views, they're providing every 2 hours of rip downs, and for REPRIS, they're providing like every 8 hours of rip downs. They're basically dumping all the connected BGP peers data into compressed files. And they're also providing like the periodical like 15 minutes or 5 minutes of BGP updates archives. So we're taking the BGP updates archives because we want to know what's going on in real time, and we don't want to the actual snapshots of routing tables not really matter to us right at this point. So we're taking the updates archive and shipping it into a kind of a processing pipeline where we do a little bit of pre-processing of the data. We're chunking, like basically parsing the data and turning it into a one Kafka stream of BGP messages. So the consumers downstream can take that messages and examine them one by one, and then do their analysis. And now we're coming to, at the core of detection or leak detection is the AS relationship inference. Or in other words, we're trying to tell between any pair of ASs on the AS path, are they peer, are they peer-peer, or are they upstream, downstream, or provider customers? And this is the core questions that we need to answer before we can even do any of the analysis. So there are multiple data sources available, like publicly available right at this point. UCSD CADA is a research lab that has been operating for years and years, and they have AS relationship inference data for years to come, for years before, and so it's still ongoing. And that data is very valuable. And then there are some drawbacks of the data because every single pair of ASs can only have one relationship. So that's kind of the drawback noticeable in this context. And then I also kind of doing a little bit of work for, and it's on like a BGP Git relationship data that is like you can have multiple AS relationships between a pair of ASs. And then we're combining those together into a initial draft version of the AS relationships inference. And that inference, because we don't actually know what their inferences or what their relationships, we can only infer. There's no public ground truth on whether two ASs are actually peers or what's their relationship with each other. So at best, we can do an educated guess. So that's why on a path like this, we're having those question marks. We're kind of guessing what are the relationship between them. And at the last hop, what we want to kind of solve at Cloudflare is that we can take care of the last hop. We can learn about, we can actually get 100% accuracy on the very last hop. So at least anything that connected to Cloudflare, we can know for sure what's the relationships given the prefix and location of the data. So in this slide, we're talking about, so starting with unicast data. So as one step back, so for each unicast data, the main kind of takeaway point from previous slides is that there can be only one pop that announcing that prefix, the prefix. And then for each pop that we're announcing the prefix, we have a list of kind of static transit providers that we can learn from a set of internal APIs. And then the logic becomes like when we look at a unicast prefix and we check out the paths, we first kind of mapping the prefix into the pops and then check the pop, map the pop into the upstreams. Then we match whether the next hop of us is whether on the hop or not. If it's on the if it's on the upstream list, we know for sure it is the upstream for this particular prefix, and that's 100% for sure. And if it's not, we know also for sure that it's supposed to be a peer. It should not be a transit provider. And given that, we have 100% accuracy on whether the next hop that's connecting to us is upstream or not for unicast prefix. And similarly, for Anycast, it's actually a little bit simpler because for Anycast, we have a small number of networks that are supposed can provide transit at all for Anycast prefixes. So it's like combining a short list of data of upstreams and then check them whether they are on the list or not for the given prefix. So combining them together, so at the beginning, we check whether it's an unicast prefix, either the ones that we announce, and then if it's unicast, we do the bottom line of checking, and if it's anycast, we do the top line of checking, and then at the end of the checking, we'll determine whether the next hop is a peer or is a provider. And this gives us the ground truth of determining what's the next hop of us. So the only potentially incorrect inference will be the next one. So what we care about is for 3 AS pair, or whether they what's the relationship among them, and whether they form this kind of a hairpin the hairpin style leaks or not, or other types of leaks. So by doing this, we're able to reduce a lot of potential false positives that we potentially can introduce just because of the complex relationships that we have with other networks. So here's some simple alerts that we had in the last week. So there's a quite large leak by I think it's an IXP. It's a Ralph Reflector company, and then they've been kind of leaking a lot of prefixes, and we got alerting from I think 5 minutes from the alerts happens. And then we have an internal Hangouts kind of group that basically sending us messages as soon as we detect anything relevant to any leaks that are relevant to us. And we start giving out more information like how many of the origins are affected, how many of the peers are affected, how many of the prefixes are affected. And then digging into any of the events, we're also providing more information to allow operators to see what's the timestamps of those leaks, and how can you actually dig more into those leaks. Like you can provide, we provide like Monaco commands so that you can actually search and get exact BGP messages that are involved in the leaks. And then we're also providing additional informations like what's potentially causing the leak. Why is this a leak? Is it because some transit mismatch, or is that something else? We're adding a lot of more tags internally just to make sure that operators like Bryton can understand why this thing is happening, and then why we're the detection pipeline think it is a leak. So given all this context, all this information, I think operators can react more faster, and it can basically make judgment call based on all the evidences and to determine the next steps of the reaction. So I'll like Bryton to talk about the features of what we think should happen in the leak detection context.
I'm going to make this quick and brief, but this is just kind of some of the RFCs or drafts that are out there that we're kind of keeping an eye on, maybe some potential there for making impact a lot less for route leaks. So emphasis on draft for ASPA, autonomous system provider authorization. Say that 3 times fast if you can, I dare you. But the general idea is you're going to create ASPA objects on RPKI with the general idea of being, I'm creating an object and I'm saying for my ASN, here's my authorized list of actual upstream providers, which is really great if you have like a tidy list of authorized providers, but Cloudflare does not. But it's going to help validate and invalidate route leaks, kind of like route origin validation does for route hijacks. Implementation status, I'm just going to leave that where it is. It's not super great yet, but like I said, still in the draft phase. There's a few names on there. We'll see where we go. So limitations are pretty obvious. There's no prefix level granularity at all. I mean, it's just if you're an ASN with relatively tidy upstreams, you can probably benefit from this pretty easily. If you're Cloudflare and you're AS13335, not so much right now. How do you get the most out of it? If you can express your BGP intent, your intended scope at the AS level, then that would be great, at least for your primary ASN. Maybe you can use an alternative origin and peering ASN for certain things to get that done. But that's kind of, you kind of have to conform to get the most out of ASPA if you want to use it. So the other is RFC9234 with BGP roles and the only-to-customer attribute. So this one's interesting, where you literally assign, it's a new BGP capability where you're assigning roles like customer and provider on each side of the BGP session, and you communicate in the open what your roles are, and then an only-to-customer attribute goes on routes. For example, if you're sending routes to a peer or you're sending routes to a customer, hey, only to customer, please, on those announcements. So kind of the same thing with implementation status. There's some names on there, but there's also some missing. But the really interesting thing about RFC 9234 is section 6 of the RFC, which is additional considerations. And in here, it purposely calls out complex peering relationships. Sounds kind of familiar with the whole theme of this talk. But the general idea is they want to leave it open for vendors to be able to have you configure within policy whether to attach only to customer attribute or not. So example, going back to the Anycast versus Unicast example, I might say to that neighboring AS, hey, I'm going to put OTC, I'm going to put only to customer on these Anycast routes because I want you to send those to peers, but I'm going to strip it on the routes that are Unicast that I want you to send to transit. So that's all we had. If you have any questions, I'm happy to take them.
Yep. Hi, Aaron Atach, Akamai. Great talk, guys. So I had a couple questions. First, it seemed like you were only parsing MRT dumps. Are you doing anything in real time? Are you reading BMP off your own routers and inspecting feeds that you get directly?
Thank you for the question. You're reading my mind.
Okay, yeah.
Yeah, we are doing some of the BMP processing at this point, and for now, this is a limitation of the current implementation. So we started with the This is a kind of a radar feature that we wanted to start for everyone. Like it's not designed at the beginning. It was not designed for Cloudflare specifically, right? So it was intended for everyone, all the ASs out there. So it's with our MRT files, but we do started to look kind of implementing features to incorporating real-time ones. So the real-time actually not only limiting to our real-time BMP feeds. We do have that. We're starting to incorporating those into the pipeline, but we're also started looking into like a RIS Live, and then the raw views has its its Kafka streams that are also started to become available. So we're kind of integrating that into this pipeline still. And then the good part is that integrating it is actually pretty simple because we have this kind of a black box, right? Some data in source and going in, and then a stream of Kafka message goes out. So we just need to add that into this Kafka message producer, and then the rest of the pipeline is still remains the same.
Okay, so my second question was going to be, are you using RightBriz or just their MRT dumps? So yeah, we're on the same page. I'll change my second question then. I am curious, are you, possibly considering doing a follow-up talk of like how Cloudflare is stopping from yourself causing leaks? Not saying that you are or that I'm paying attention to anything, but that we're all network operators in this room. We all make mistakes.
So
It's one thing watching other people's, but it's another to learn from lessons internally and possibly share that with the community. Yeah.
yeah, so from an operator perspective, unfortunately, the leak detection that we have has caught a lot of misconfigurations, and it's really great because we were blind to these things before. It's like, oh hey, I was advertising this unicast prefix destined to London, but I was advertising it to Telstra in Asia, and I didn't mean to do that, so that's not great. There's some suboptimal routing going on there. So haven't considered a talk on that, but I appreciate the shout out because there's definitely some of that happening.
Lastly, I know ASRank had an outage a couple months ago for a few weeks. I was curious if you noticed that, how you reacted to it. There was a bit of buzz on the NANOG list about it, but it's a very important resource that a lot of people depend on with educated guessing in mind. But when it goes out completely, I'm curious how you react.
Yeah, who was that with the outage? Sorry.
ASRank, KEDA had an outage about a couple months ago for about a week or two.
Right. So the thing that we when we started building this, we kind of the first step we do is to archive data like locally, right? So that's like trying to reduce the third-party dependencies as much as possible. But I actually don't know about the ASRank the outage, but I did notice that one day, but it was not critical to us because we kind of already synchronized the data first. And I think for ASRank or for the data that we're interested in, it's generated like either quarterly or monthly, so it's not that frequent. So, but for other data, we try to actually work with them to try to see if there's a possibility to, I don't know, synchronize data and provide more help on that. But
just curious how you implemented it. Good. Thank you.
thank you.
Hi, John Christoph. A question about how you might address what I think might be certain challenges in your leak detection. So the two use cases I was thinking about, or two cases where I would imagine maybe there's some difficulty in determining whether it's actually a leak or not. One would be when you have DDoS mitigation providers who actually announce prefixes on behalf of some customers. I think most of them tend to be good about, pre-publishing ROAs, but maybe not. You may be able to tell something different. In the other cases, maybe another example case would be when the IP address leasing organizations like an IPXO, or those organizations, because their prefixes move around so much, sometimes they probably have customers that are no longer supposed to be announcing prefixes due. So what have you encountered that sort of thing? How do you deal with it? What sort of issues like that do you have to work with?
Thank you for the question. So for both cases, I think it mostly falls onto like not just raw leak, but a specific raw leak that relevant to the origin of the prefix, or at least for the like and the leasing companies they're changing origins, right? So those sort of cases we do capture that quite a lot, and then we do started to adding labels to try to avoid like generating excessive alerts, just because the nature of those this type of operations can can trigger a lot of false positive because the delay of multiple data sources. Like for example, for leasing companies, IP leasing, that there can be delay of like RPKI synchronization, right? So they lease to a new company, they start originated, but their RPKI like ROAs haven't been pushed out or been synced to like different sources yet. So we see that as a RPKI invalid announcement, but then like 5 minutes later, it's become valid. So we are aware of this problem, and then we try to add in more context or labels to reduce, for those cases, we're reducing the confidence scores, basically, because they have certain reputations or kind of context behind them, right? But it's a great question, and we definitely see that problem in our detection system, yeah.
I had two questions. The first one you already answered just now. Second one is there any requirement or enforcements to your peers with regards to ISPA and RPKI, since it's been around since pre-COVID?
Yeah, so do we enforce RPKI for origin validation? Yes, we do. But
Okay.
for route leaks, or what do you mean? Like we do peer lock, this type of thing, but what do you mean from an RPKI ROA and origin validation perspective? We enforce all of that. Yeah.
Okay, that was my question.
Okay.
Thanks.